Welcome everybody to the presentation of the position paper of the Task Force Sustainability, and it's my great honor to present this also in the name of the co-chairs Peter Fischer and Antonio Martinez. That is actually not the first time that we present the results or our thoughts regarding the topic of sustainability. We were invited by the World Circular Economy Forum just already in April and presented and even discussed that broader topic of sustainability. And second, also, I would say, 2 weeks ago, there was also in Brussels the Batteries Europe BEPA meeting, and so we presented also here the outcome of this position paper. Just regarding the outcome and the background and the main objectives. That the base of this work was actually a first position paper from 2021. Actually, at this time, that was a rather small group, and a nice activity, but was just the starting point. But now, based on that, we did now some improvement and also broadening the topic, and especially considering also the new framing conditions. And what are the new framing conditions? That's for instance, the Critical Raw Materials Act, paper Safe and Sustainable by Design from GRC in ISPRA, and the Net Zero Industry Act, and last but not least, especially the new battery regulation, including the battery passport. And the objective was to give a comprehensive look on the topic of sustainability for present, but also especially for emerging batteries and along the full value chain. And that hopefully helps then to create ideas and to see and find option to develop a more sustainable batteries ecosystem in the future. Now, the structure actually is rather simple, I would say. First, in the position paper, we focused on the new regulatory frameworks. Then we had this 3 dimension, the economic, the social, and the environmental sustainability as a broader summary or the broader structure of this topic. But more importantly, that we say this kind of sustainability assessment has to be considered from a life cycle thinking perspective. That really starts from raw material extraction, the design of the technology, the production, the use phase, second or third use phase, and last but not least, recycling. And because of this life cycle thinking, of course, especially design aspects are quite important, because in the end, the design of a technology determines in the end also the use phase, but also the options regarding recycling or second use. Just coming already to some summary key points of the paper, and we totally agree that the battery regulation, including the battery passport, that are really the most important guiding framework at present for this sector, including for instance, the recycling targets, even if they could be even challenging in the future, but that we will see how this sector will also develops in the future. Then we already said regarding the battery passport, for instance, that CO2 footprint is a nice starting point, of course, but there should be in the future also to include more indicators, because otherwise there could be the option that if we only focus on the CO2 footprint, that we ignore, for instance, the resource demand for technology or toxicity aspects. So we have to start with the CO2 footprint at present and in the close future, but then this should be enlarged and broadened to broader perspective. And also we see in this battery regulation, battery passport, that the second use of batteries are at present not well addressed, that even here we need some further development of these 2 structured papers. Yeah, and the topic sustainability, as his natural, that is a cross-sectoral, cross-cutting topic, and yeah, of course, addresses the economic, the ecological, and social aspects, and that is sometimes even difficult because there could be even some conflicts. Yeah, maybe one technology is much better from the economic perspective, but there's maybe some shortcomings regarding ecological aspects or even toxicity aspects or social aspects. So that really we have to address in the future much more these conflicts, not only to display it is one thing, to display potential conflicts, but then also to yeah, provide some guidance how we could solve such conflicts.
Marcel, sorry, you are muted. Suddenly you are muted.
Okay, sorry. So I tried again. Okay, regarding the economic sustainability, there, of course, the life cycle costing is the tool which we would prefer from a life cycle thinking perspective. But of course, there are also others which we can consider, and also to maybe include externalities, costs, and to assess the different technologies. The market is, of course, quite important, how this market will develop and maybe what are the most important technologies which we have to focus on. Resource criticality is a big issue, so supply risk and maybe some the provision of some regional resources in the future, and last but not least also, of course, recycling. From social sustainability, then, of course, again, from the life cycle thinking perspective, the social life cycle assessment is here the most sophisticated tool. There are still some problems with the database. The methodology is there, but the database is quite critical, I would say, to do really some reliable and transparent assessment. But on the other side, there is, of course, the social life cycle assessment is only one way to assess the social implications. There should be also in the future the consideration of some more qualitative social indicators, and that is, of course, is a certain challenge. And therefore, I think here we have a really nice link to the Task Force Social Science and the Humanities, which will, after this session, will have their own session and maybe address this in much more in detail. Last but not least, the environmental sustainability. Here again, the LCA, the life cycle assessment, and in the moment, at least for the batteries passport, the CO2 footprint is very dominant. As I said, we have to include much more indicators in the future. From a scientific point of view, that is quite common, but here in the regulation, in the moment only they are asked for the CO2 footprint. Toxicity is sometimes it's a tricky topic in a certain way, how to assess in a really good manner the toxicity of technology, and sometimes even there could be even some topics which maybe are not so much focused in the past, like the PFAS. I will focus on that a little bit later. The resource demand is critical. If we would manage in the future the demand in battery storage only by lithium technology, there would be some shortcomings and some pressure on resources, and maybe then also some strong increase of the prices for these resources. And therefore, of course, also to look for other technologies like sodium, potassium, magnesium, which maybe what could that maybe a potential option in the future. Second, use and recycling in the sense of circular economy, quite important. We have to address that much more than in the past. And then last but not least, the methodological challenges, not only for LCA, even for the whole sustainability assessment, we have to address much more in the future and maybe especially have some harmonization in this manner. Yeah, as I already said, we just for this presentation, I selected this as a specific topic because I thought a little bit, we missed this topic in the past, yeah, the PFAS. And I said even in Brussels, maybe I would say we missed a big elephant in the room, yeah, because the PFAS are now all over. They are not local emissions, which would say there are local problems. Yeah, no, they are all over. Yeah, they are on the ground. They are in the rivers, in the lakes. They are even now found in the groundwater in many locations, even in Brussels. Yeah, so even here in the Rhine Valley. So we have to address this topic. Not only for batteries, that is of course true for all technologies, and we have to find ways to deal with that. And there is a lot of unknowns still with the PFAS. That is the problematic. There are only some indications for some PFAS that they are toxic. For the rest of the groups, there's only little knowledge. So even there, we need some improvement and more knowledge. How critical are PFAS and which PFAS exactly? Maybe there are some PFAS which are not so critical. So we have to learn much more, and we need more information regarding that topic. From a battery perspective, we said we have to deal with that, and therefore we suggested two approaches to which should be necessary to address, to at least from battery perspective, to improve the situation. And that means for the existing batteries, we have to develop the recycling process in such a way that there is no way that the PFAS enters the environment. That is one important point. And the other important point is for all the future batteries, we have to at least reduce or eliminate the usage of PFAS, that we have there no problem in the future, or maybe a closed cycle of the PFAS. That could be also an option there. That means with these two approaches, we think at least there would be one step forward, but that means we need some more research and development in this area. Coming to the conclusions, as I said, there should be the development of a common assessment route for the evaluation of batteries, that focusing on the social aspects, the environmental aspects, and the economic aspects over the entire life cycle. And that should be applicable to all chemistries, or maybe then even for other battery types, like for instance, flow batteries. Then also to ensure the uniformification, I would say, regarding the reporting of environmental performance, define standards for transferring and handling of the sustainability data, especially then if we use such a data for the assessment of technology. And then, of course, here are nice links also to the task force digitalizations. Then from our perspective, then to develop guidelines for improving sustainability assessment of the battery production and the recycling process, and maybe support even some, very similar to best available techniques as a model, that to support such a positive development. Then promote environmental friendly production, and also to protect the employees and the societal welfare. And last but not least, and that I think it's quite important, it's maybe the example could be PFAS, to engage the industry, the academics, the NGOs, maybe the environmentalists and societal stakeholders, and to discuss and potentially solve the potential sustainability conflicts and bring it forward to hopefully to a certain solution. But of course, there will be potentially some trade-offs. So that would be from my side regarding the position paper. And at the end, of course, I would like to thank all the contributors of the Task Force Sustainability and the support of Batteries Europe and BEPA. That's from my side. Thanks a lot.
Okay, thank you. Thank you, Marcel. Now we should have Mr. Rana Pant from European Commission. I don't know if he was able to join yet, Mr. Rana. Maybe not. So I would ask to Jens Peter can anticipate his talk. Jens Peter will from University of Alcalá will discuss a very hot topic now, that is the first draft for the carbon footprint calculation. Jens, could you share your screen, please?
Yes, I will try. You're too quick now because I see that I couldn't test it because I just need to switch the monitors, because otherwise it will be you will see the referee view. So I did not expect. I did not. Well, I have 15 minutes extra now.
Yeah.
Okay, just 1 second. Okay, that looks good. I just need to sorry, just share my screen for a second. And this will be this one. So you should be able to see my screen now.
Yes.
Okay, that looks good. Very good. Okay, then yes, thanks for being here. And maybe I will need to add some information, because I was somehow relying on the input by Rana, who would also talk about the regulation. So I will have to maybe take some few minutes extra. But anyway, I think that should be fine. So I'm going to talk about the carbon footprint calculation as it is currently published. So I will take the university hat. Now I will talk about the official information that is here, about the methodology, about the background that is, and the challenges that are actually to be found in this realm, and also the limitations, no, because we're talking here about the sustainability and about the task force sustainability, and also making the link with the social science and humanities to see what needs to be tackled here beyond what we already have on in the acts, no? So what do we have? I have some weird animations here. I didn't want to put these. So we all know, I think this would be the introduction that I want to be quick on. Batteries are one of the key technologies. No, we are all aware of this. And we have these high growth rates of like 20-30%, which always, for me, is something that rings a bell when you're like working in sustainability. No, any technology that grows with these rates is some kind of a Wild West. So we really need to be careful about putting sustainability into the focus, not to keep this kind of development in sustainable on sustainable tracks. Therefore, also batteries are one of the key sectors of the European Green Deal, and this is why there's a lot of regulation being done around all these aspects. And the batteries regulation, I think, points out, or is something really to be named as some kind of highlight, because it's I think the first regulation that really puts a mandatory life cycle based carbon footprint declaration to a product. So therefore I think quite interesting, and also there's a lot of interest, I think, from all kind of different sides and stakeholders. So how does it look like? We have the battery regulation here, published in July last year. That is, I think, well, present or known to most of you. You can just download it here. And we have some important aspects here. If you download here, these different articles that are appearing in a very weird order. I don't know why. So first, we have the carbon footprint declaration, which is what I'm going to focus on. But there are also many other aspects that actually really try to put these batteries to foster sustainability. No minimum durability requirements. We all know from a circular economy aspect, product durability is a key. So it really tackles durability of the batteries. It requires the batteries to disclose information on their expected lifetime and state of health to foster repair and reuse of the batteries. It establishes minimum collection targets and recycling efficiency, which is the part that Rana would talk about, to support a circular battery economy. We have the battery passport that puts it all together, that requires each battery to be accompanied with a battery passport that contains all this information on the carbon footprint, on the durability requirement, and so on. And we have another part, which is the recycled content, which also is part of the whole bunch of measures that try to make the whole battery sector more circular, in this sense. The battery regulation is already here. We have it since July 2023, and this comes then also accompanied with several delegated acts that actually put the articles of the battery regulation into legislative text, no? Because the regulation is quite coarse. It's just some very general requirements, and then we have this delegated act that actually put them into practice, where the methodology is described. For the carbon footprint, this looks like you see here. We have the electric vehicle batteries that are due, where the delegated act that actually publishes the methodology should be published in February 2024. We see that it's already delayed. We're running late on that, so it will probably come after summer somewhere. So we will see here. So there's a certain delay, and corresponding afterwards, the same or similar delegated acts for industrial batteries, light means of transport batteries, and then industrial batteries with external storage, which would be flow batteries. Industrial batteries here is a very broad field that contains everything that is not contained in any of the other categories. So it's really everything from an airplane battery to a ship to a stationary storage system, a huge one, to a home storage system, anything. So a very broad field, which is actually quite challenging then to put into under one roof. And then afterwards, you have this mandatory declaration of the carbon footprint, which comes about 1 year or 18 months, depending on the battery technology afterwards. So then these batteries need to declare their carbon footprint mandatorily. So they have 1 year from the publication of the methodology until this declaration becomes mandatory. And the same year, then there will be a second delegated act, legislative text that establishes the performance classes, no, like A, B, C, D, G, whatever, that puts the batteries into different performance classes. This is still future. The background behind all this, what is this carbon footprint declaration based on? It is essentially the PEF method, no, the product environmental footprint and the product environmental footprint category rules developed by the Joint Research Center of the European Commission since years. We have a very detailed methodology here that actually puts all the activity that has been developed within the ILCD, the International Lifecycle Data Network Initiative, that many of you, I guess, know from all these CITA conferences and so on, that have been like screening, putting together the best practice in literature on life cycle assessment, and put this into these recommendations that actually provide a very detailed guidelines on how to develop product environmental footprint category rules and product environmental footprint. It's a very detailed framework, quite complex, and sometimes it is also not really clear because it's some kind of an academic exercise up to a certain point, and this is why for the battery regulation we need this to be more precise, and because finally you will have a carbon footprint and a carbon footprint class, so you need to be comparable. You cannot be ambiguous in this kind of methodology. This is why the carbon footprint declaration needs to be more strict and more normative than these product environmental footprint rules are. But this is the basis, and if you read the carbon footprint rules, you will see many of the aspects that are actually defined here. You see them appear again because this is all based on this methodology. So what do we have? We have here this carbon footprint rules report, because the contribution or my talk is about the current draft. Now, because we have several drafts on this carbon footprint rules, which is a little bit weird in this sense. We have this one, which was the JRC report from last year, from June 2023, which was the first attempt to put this into it's not a legal text because it's just a report, but that describes the whole methodology for the electric vehicle batteries, how to determine the carbon footprint. And this was then the input for the delegated act, which is actually now currently available on Have Your Say on the platform by the European Commission for stakeholder feedback. Unfortunately, stakeholder feedback just closed on 28th of May, just 1 month ago, but you can access this delegated act, which is actually the legal text based on this document here, right? This document took around 1 year to cast this into a legal text with all this stakeholder feedback that has been provided so far. And this is actually the latest official document on the carbon footprint methodology. Okay, I will talk on some key aspects of this just in a second. But you will see if you read them and compare them, these two documents, that they are quite different. In some aspects, some methodological aspects differ quite substantially between these two documents. So there has been an evolution and some changes, and this needs to be considered when trying to calculate it. This is still not an official document. This is open to feedback, or was open to feedback. You can also look into the different feedbacks that are provided here, and you can have an idea of what will happen with this. So we can expect this maybe to come out after summer, somewhere. I don't know when. So let's see. So what is the important or the most important aspects here? Well, one point maybe before I go into this is this is for the electric vehicle batteries, right? So very, very important, because we have these different battery classes, electric vehicle batteries, industrial batteries, light means of transport batteries. What we have here in this delegated act is for the electric vehicle batteries. There's another report. This is just recently being distributed. This is another joint research draft report for industrial batteries, who will come 1 year later, right? So in theory, in 1 year, there will be another delegated act on these industrial batteries. And this one will be available, I think, from next week on the webpage of the JRC via the EPLCA. So you can check here the link with this QR code if you like to. And there's going to be a stakeholder consultation on the 8th of July. So anybody who's interested in this and contributing to this and listening what's going on there is invited to participate in this stakeholder consultation on the 8th of July by registering here via this email. For the industrial batteries, what I'm going to talk now is about the electric vehicle batteries, because this is what we have currently officially published on Have Your Say for the Delegated Act. And we have here some key aspects that I would like to point out, which is the system boundaries, the modeling requirements, functional unit, electricity, and end-of-life modeling. I try to be quick, so as far as possible. So this is all based on this information here in the Delegated Act. We have, for the carbon footprint of the battery, we have the use phase of the battery explicitly excluded, which is like this specified in the batteries regulation. So there's nothing to do about this. Use phase is excluded, and we have some core processes, which is the battery production, the cathode production, the active material production, which are the main components which have to be modeled mandatorily by company-specific data. So you collect your data for your production process, energy input, all the material inputs, and model a process, an inventory that you then combine with secondary data from the database that is provided for this carbon footprint. Okay, so this is a modeling based on primary data, and then you have a collection of most relevant processes where you are allowed to model also the upstream processes based on primary data. But it's only a set. For example, the key metals, cobalt, nickel, lithium, titanium, graphite, then you have copper, aluminum, steel, where you're allowed to model your processes also upstream based on company-specific data, while for all the others, for example, plastics, you're not allowed to model anything based on primary data, on company-specific data. You're obliged to use the secondary data that is provided in the data sets, in the carbon footprint data sets. And this is also the modeling hierarchy that I put here. This is for these most relevant processes that I've been talking about, cobalt, nickel, lithium, which is the key metals where you all know that is causing the key impacts of the batteries. You have two options. Either you pick a secondary data set from this carbon footprint data stock, which is a data stock where all these secondary data should be provided free of charge, so you can use them for your carbon footprint declaration. Or you can create an own data set. And for all non-most relevant processes, for example, plastics, the separator, and so on, you would use mandatorily the secondary data that you find in this carbon footprint data stock. So what's going on with this carbon footprint data stock? There is no carbon footprint data stock yet. So everybody looking, well, how can I model this? I don't know, because there's no carbon footprint data stock currently yet available. Now you have this delegated act that's supposed to give you guidelines, but you don't know which data sets to use. You can, however, look a little bit into the PEF method, and you see that there is this EPLCA node, which is also referred to in the delegated act, where you find the different nodes of the different data providers. So you find here the EF datasets for the environmental footprint method. So for any product environmental footprint study, you can use these datasets, and we can maybe assume that the datasets for the carbon footprint will be the same, but we don't really know them. So currently you can access these datasets via these nodes on the European platform on LCA. You get access to these different nodes, and you can download these datasets to your computer, and you can import them into your lifecycle assessment software. This does not always work because they come from different providers. They're not compatible, not totally at least, so you will have problems. Well, what do we do? You can go to a software provider such as SEMA Pro or Green Delta. They have these datasets already pre-processed, so you can import them. You pay a small fee for this additional effort they do, and then you have the dataset at least working. So you have them in your software, and you can use them. But then you look at the end user license agreement conditions, and this is not at all clear. So for example, if you go to this node here, this is for Sphera, which is one of the providers for these environmental footprint datasets. You go to the Sphera node, this looks like this. You have to register here. And if you register, you can access these datasets. Usually they give you access. You can download these EF 3.1 datasets, which are valid until 31st of December 2024. Which is just when the carbon footprint declaration becomes mandatory, in theory, or the year after. So it does not really fit. Then you look into the end user license agreement. So they say these datasets are used as free of charge exclusively for PEF OEF studies under any of the European Commission's official PEF-CRs. So they don't say anything about the carbon footprint declaration. So we don't really know if these could be allowed to be used or not. So it's not clear. If you go to EcoInvent, for example, that's another issue. If you want to download this end user license agreement, it just does not work. The link, so something else. If you go to EcoInvent, which is another data provider, you will find the validity until December 2025, so 1 year longer. And here you have a different end user license agreement where they say it can be used in compliance with the requirements of an EU policy. So this sounds more like as if I could use them for the carbon footprint study. For me, it seems like this. But still, this is just a subset of the datasets because we need to combine both, because a part is delivered by Sphera, another comes from EcoInvent. So there's a big uncertainty around all these datasets. This is the first big question we have here. So there's no solution around this, but there's supposed to come something hopefully soon. Second, interesting electricity modeling. We have here some interesting, I mentioned this rather because it's quite a big change we had in this JRC report in the beginning, based on following the PEF recommendations that we have, the inclusion of power purchase agreements. So you can buy green certificates, green electricity, and claim this green electricity for your carbon footprint under very strict conditions, stricter than we had in the PEF recommendations. So there were some additional requirements to really ensure that this would be controllable and to disclose the residual mix and so on. But if you now look into the Delegate Act with the new document, there's no green electricity anymore. This was completely kicked out, and you can only use the national average electricity consumption for the carbon footprint. So huge, drastic change. And if you look at the stakeholder feedback on Have Your Say, there's a lot of comments on this. Some people are very happy, some are not very happy. So it's essentially a political decision here what is being done. But currently, this is the last situation: on-site average electricity. Functional unit is another very interesting aspect because the carbon footprint is declared per kilowatt hour of electricity provided by the battery. So the big challenge is how to determine the amount of electricity that this battery will actually provide. In this JRC report, there was the total energy to be determined based on the energy consumption of the vehicle and the declared lifetime of the battery until reaching a certain state of health. This was based on some standard, the UN GTR standard. So it was based on the vehicle. And now, if we look into the Delegated Act, this was the wrong direction. The thing changed totally, and now we have a functional unit, which is basically the energy capacity of the battery multiplied by the years of operation. There's a fixed factor, which is like the average cycles per year. But since it's a fixed factor that is applied to any battery, it somehow does not really change anything. So essentially, it's just capacity over years. So it's not anymore really the energy that the battery provides, but it's the capacity the battery is able to provide over a certain number of years, but based on the manufacturer warranty, which is somehow a smart solution because it rolls back the obligation to verify all the number of cycles back to the battery manufacturer, to the car manufacturer, whoever gives this warranty, and at the same time incentivize longer warranties. No, because if you declare a longer warranty, you have a higher denominator, and your carbon footprint will become comparably lower. So this is somehow the background behind this. But there's very drastic change here from one document to the others, and it's interesting to see how this suddenly appears, and we don't really know why. Another important aspect is this end-of-life modeling, which is quite complex because of this circular footprint formula. We have a default recycling process, which is mandatory for all to model this recycling process, which just recovers 3 materials, copper, nickel, and cobalt, which is a pyrometallurgical treatment. And you also have a return rate of a certain amount of batteries that are actually not recovered, because these are the batteries that are exported, and some are where you assume that these battery cells are not actually recycled. So this would be the default recycling. You're allowed to model a different recycling process if you can prove that you will recycle your batteries with this, but by default you have to use this default one. And then we have this strange and very much infamous circular footprint formula, which is really a big mess. I put this here just to show that it's really complex, and nobody seems to be happy with this, because all the stakeholder feedback that you see on the platform, there's a lot of people complaining about this, that it's very complex and incomprehensive. And I will not go into detail. The thing is that it somehow tries to bridge the 2 approaches for allocating end-of-life impacts. So this would be, for example, you have one option which is a credit, and one option is the cutoff approach. So you can either account for recycled content in the input. You say I have secondary material and I account for reduced impact of secondary material, or I account for a credit at the end of life. And with this A value, you can actually change the allocation between a certain, it always considers both aspects, but with this A value in this circular footprint formula, you can somehow allocate more weight to the end of life of the recycled content, or more weight to the production side, the recycled content that you have in the battery. The whole thing is super complex, as you can see, because you have to mix the input. You cannot, if you have a certain amount of virgin material, you always have to account for a certain amount of secondary material as well, because of this allocation. So it's very complex, and it somehow is challenging, because you don't really know how the recycling process looks like at the end, no? Because you somehow have to model a process that is going to be in the future, and you allocate a certain amount of impacts to this future process that you don't really know yet. Therefore, there's a strong position towards this cutoff approach. You say just account for the recycled content here, because it's easy, it's simple, you don't have this formula, and it might not be totally correct, but at least it's feasible. And like this, it's quite complex. But this is what we have currently. So this will be probably, as it is now in the delegated act, will be like this. So we have to deal with this. This is good for consulting companies who want to do these carbon footprint declarations for other companies, because there will be knowledge on this. And this is all. I think how I'm going on time. I think this is just the 15 minutes. Yes, this was all on the methodology. This was a very quick going through this. What I want to say, because we're here in this task force sustainability, and later Vera and Adam will introduce the social science and humanity task force. We have a very ambitious and very complex framework for this carbon footprint declaration, which is like at the forefront of legislation. I think we can be really proud on European level, despite all these insufficiencies that this legislation has. But it is really a forerunner in terms of environmental legislation. But it's just the carbon footprint, and we have much more. No, we all know we have issues of acceptance, we have issues of local mining, we have issues of social life cycle assessments, where all this stuff comes from, right? We have issues of externalizing environmental impacts to other countries. We have issues of this recycling, that batteries disappear and we don't really know how these are recycled under which conditions. And we have other issues that are related very much with social science and humanities, because we're talking about a circular economy. We're not talking about a circular product. We're talking about a circular economy, and this includes consumption. This includes consumers and behavior. No, and this is also the aspect that we need to go a little bit beyond just a technology-centered approach, carbon footprint declaration, but also the amount of batteries, the kind of batteries that we actually need. No, do we need these huge batteries? How much electrification do we need, and how much mobility? So this goes much beyond what is actually a carbon footprint and even what is Task Force Sustainability currently. But I think this is something we need to look at also at the broader picture. No? And this is what I want to conclude with. There's still a long way to go. We have some really beautiful environmental legislation in Europe. I think we can be proud of what's been done there. Very ambitious legislative frameworks here in terms of reducing the impact, closing the material circles, also tackling social impacts. But finally, where we want to go is this, right? So it's not just about making one technology a little bit better, but we have to finally live within these boundaries, no? And this should be the final objective. And this is then maybe the outlook where we could think about these different task force, how we can I don't know, hook up with these objectives that we have here in this sense. And yeah, that's all from my side. Thanks a lot. And then I'm going to pass the word on to, I don't know, the next speaker.
Oh, thank you, Jens, for your super presentation, which will reflect the complexity and the challenge behind the numbers, but really, really clear the route. Does the audience have any question that you would like to anticipate, considering the hot topic now? Please, Edel.
Could I just get maybe a little bit of clarity on what you said about the energy usage? Is it in the actual production of the cells that it doesn't, they're not taking into account how the energy is produced? Is that the particular argument there?
No, the point is that it is it is taken into account. So it is taken into account. So you consider the electricity and all the energy you require for producing the cells, for producing the materials, for producing the cathode active materials, but you're not allowed to use any energy certificates. So you're not allowed to claim any green electricity. You're not allowed to buy green electricity and claim this as renewable energy. You have to use the average national consumption mix.
The average national consumption mix has to be used.
So this would put like in favor, maybe France, Norway, all these countries, Spain, countries that have already comparably clean electricity, and would put in disfavor Poland, also China. So
just to follow up a little, so if I'm setting up a gigafactory, which I'm not doing personally, but if I'm setting up a gigafactory and I decide to put wind turbines outside, that doesn't really make any difference because they're not the national mix as such.
Exactly, but it is allowed as long as you have your own wind turbines or your own PV plant that is directly connected with your plant. This you're allowed to claim, but you're not allowed to go to the electricity grid, connect to the electricity grid, and buy some green electricity from whatever provider.
Okay, thank you for that clarification.
But this is based on the Delegated Act document that is currently. Or that was under public consultation. No, this is not the final. It is not the final legislative act. So we don't know. There might still be changes. We don't know.
Yeah, this is very interesting. Thank you for that clarification. That was it's quite important to understand that, I believe.
Can I ask another question?
Yes.
Sure. As far as I understood it, you said that the use phase is generally not included.
Exactly.
Yeah, so the efficiency of the battery and this kind of things are not included in the calculations.
Are not included, exactly.
Okay. Thank you.
Antonio Valente, please, just the first hand raised up.
Yes, thank you for the floor. Thank you, Jens, for this very informative and clear presentation. you the carbon foot in the circular footprint formula. Sorry, can you hear me? I see you are.
Yes, a bit interrupted.
Yeah, sorry, I guess there is a connection problem here now. Well, I shut off the camera. But you mentioned in the CFF that there would be the possibility to, in the final delegated act, to have the cutoff approach, basically the parameter A equal to 1, correct?
No, I have no
okay.
idea what will be. First, I have no idea what will be in the final delegated act. I just I just know what is on the platform for public consultation. So this is what we have currently. There, the A factor is fixed and set to 0.2 for almost all the battery materials. So that means giving a comparably high weight to the credits at the end of life and a low weight to recycled content in the input.
Okay, understood.
Okay.
So thanks for clarification. That was a misunderstanding from my side.
Exactly. If you build a battery that uses 100% recycled material, the circular footprint formula as now, as it is in the current document, will allow you to account only for 20% of this recycled material and 80% of virgin material, despite of having 100% recycled material, because it obliges you to do this allocation, and 80% is the credit at the end of life. It's a little bit weird, but that's what it is. Yes.
Thank you. Thank you.
Okay, Xenia Kista, just last question, then we can continue later
on. Thank you very much. It's in fact Catherine Leenaerts who asked this question, but we are both of us in the meeting. Indeed, I'm a little bit worried about indeed the calculation, because when we sell circular batteries, we say that it's 80% benefits CO2 because you don't have to mine all the materials. That's one point. And the other point, when I see your LCA, there is, of course, it will be difficult, but a part of the batteries, more than 30% in Belgium, we give second life. We have a circular life for these batteries, which is not taken into account in the LCA. How can we work towards this repurposing? Because this is really circularity and is really pushing. So we should try to make kind of factor in the end of the calculation that if repurposing or second life of this battery is established, that you can, I don't know, you can have another calculation or another lifetime of the lifespan can be longer or whatever, because this is not promoting otherwise.
No, currently it is not exactly. But this is already the battery regulation. The battery regulation in the Article 7 for the carbon footprint says explicitly repurposing is out of scope of the carbon footprint. I assume this was not to make things too complicated, but it is explicitly out of scope. So this is something that is there's nothing to do about this anymore. So this can be questioned, sure, and on academic side, we can work on this. We can do assessments. We can provide evidence that this is important, and eventually this will be taken into account in future, whatever. But currently, it is out of scope. So this is
that's one of the weaknesses that Marcel Weil already also mentioned in the beginning, that there is no clear clear legislation or norms about this repurposing, which is really there we could make a difference in Europe.
Yeah. But the question is, do you need to repurpose? So if you have a battery that has a warranty of 20 years, then it will have a very low carbon footprint because you have 20 years of warranty. And then this battery maybe does not need to be repurposed because it already lasts 20 years and it will be at the end of its life. No? So if the application uses the battery until its end of life in the primary application, maybe there's no need for repurposing. So there's a lot to discuss around this. I agree. But for this
carbon footprint, car manufacturer will warranty 20 years of first life. And there is also no car manufacturer that will add in his warranty, I say 8 or 10 years first life and then another 10 years in second life. So this, I don't see there something that will help.
No, I don't know. Currently, they warrant 8 years. Some warrant 10 years. No, if you warrant 2 years more, your carbon footprint decreases by 20%. So if you have some carbon footprint classes and thresholds, and you want to reduce your carbon footprint and become better, then you maybe give longer warranty. No, I don't know. So
yeah. But the point is, there's a certain disbalance. Yeah, that means the second use in the moment is not appreciated in the right manner. That is, and then it's in a disbalance. Yeah, and then we talking about circular economy and say, oh, second use is quite important, but on the other side, it's not recognized here in the regulations. Yeah, and that is a disbalance. Agree. That means that what we discussed already with Rana Pant, that we should really maybe discuss it on this higher level, because this should be included. Otherwise, it's in disadvantage to second use, which is a high-flying topic for the EU. That is something. Yeah,
I agree, but the same happens with the recycling, no? Because recycling is equally important, and you have a recycling process in 20 years, or in 15, or in 10, I don't know when, and you have to model it today. So, and you don't really know what happens in these 10 years. Do you know what happens in 10 years with these batteries? We don't even know how long these batteries last, no? If they will be, if there will be second use, maybe these will be simply used 20 years in the car, and then will be recycled. We don't know. So it's a good question, but yes, there's a lot of uncertainty around this. I agree.
Okay, thank you, Jens, and also Marcel for replying to the question. And now I will invite Christina Minke from Technical University of Clausthal, so we can skip to another topic, that is the life cycle assessment of redox flow batteries and how to expand the digital passport to the external storage technology. So please, Christina, if you wish to share the screen.
Yes,
The is your...
I try to share, this one. So, do you see the slides? Okay. Yeah, thank you for having me. And I will refer to some important aspects that we already heard, but this is, so to say, an add-on, because I will talk about flow batteries. Flow batteries are another option for energy storage and batteries, and I think the talks before were on lithium-ion chemistries. And these flow batteries, or redox flow batteries, RFBs, are another option. And at the moment, it seems that they are not necessarily part of the legislation that we're talking about today. I will talk about life cycle assessment and flow batteries and options towards flow battery passport. So at my group, we do a life cycle assessment of flow batteries for some 10 years. And initially, we started together with Marcel Weil and Jens Peters. So this is a good match today. And we have some technical characteristics in flow batteries. And so I will first introduce the flow battery to you, because I don't know how familiar you are with this type of battery. So first of all, you see the schematic here. And you see that we have these external tanks on the left and right-hand side, and in the middle we have the cell. And this is a big difference, because the lithium-ion batteries have always the integration of the electrolyte and the place where the reaction to charge and discharge takes place. So this is always integrated, and that is why your battery goes low even when you do not use your device. And for flow batteries, it's different. We have a separation of the cell and external tanks with liquid electrolytes. And these electrolytes are pumped through the cell. And this is why we talk about flow batteries, because we have this flowing electrolyte. Here you see the discharge duration and the energy capacity of batteries. And lithium and flow batteries have almost the same energy capacities. over a broad range, and flow batteries are typically more for day storage, let's say, for a longer duration, and there's a tendency to more stationary storage, while lithium batteries are more for mobile applications. So the most commercial application is the all-vanadium flow battery. You can imagine that we can have different chemistries, different active materials for batteries and for flow batteries too. And the commercial one is the all-vanadium flow battery that you see here. But the characteristics are the same when you use other electrolytes. So we have two external tanks on the left and right with two different electrolytes. And in this case, we have vanadium ions on both sides. So we have a very, very low self-discharge, and other cross reactions or side reactions do not take place so intense as if we had different electrolytes. So this is why this type of flow battery is very widespread. And in the cell, you have like a usual a battery cell with a membrane, which is between these two half cells. And in the half cells, we have this felt electrode, so porous or another kind of porous electrode where the electrolyte is pumped through. And this is, for example, such a felt electrode. This is very high porosity, and so the electrolyte may be pumped through. Flow batteries are for megawatt applications and at very high cyclability, like 15,000, 20,000 cycles. So we have this long lifetime here, which is calculated to be 20 years at the moment. Nevertheless, warranty times when you look for commercial batteries are lower, of course. We have a special characteristic for flow batteries, which makes even LCA calculation very complex, because we have this independent scalability of power and energy capacity. So power is scaled by the electrode areas, and the energy capacity is scaled by the size of the tanks, so by the electrolyte volumes. And this is independent. As I said, in lithium-ion batteries, it's integrated, so it's not independent. But for flow batteries, this is independent. And so you can imagine we have a very wide variety of different combinations of energy and power. Another aspect is that flow batteries, as long as they are using aqueous electrolytes, they are inherently safe. So they are non-flammable, and this is another aspect that's different for lithium-ion chemistries. They have a very high potential for reuse and recycling of the components, and this will be striking when it comes to LCA. So I said we have a wide variety of flow batteries. So first of all, we have different electrolyte chemistries. So we have vanadium, but we can also have other chemistries at the moment. Iron batteries are a very hot topic because they are very low cost and easy to recycle and everything. But we have zinc, bromine, and you can imagine many chemistries. So this is the first thing. And the next aspect is the design of the battery cells. So this is like you see here some matrix with different characteristics and different use cases. So for more residential use, or for industrial large-scale use in the megawatt area, we have find typically two different cell areas. So we can have cell stack with very small single cells, and there are systems using very large cells with about 3 square meters per single cell. So this is a real scale up in power here. And then we can add on a numbering up, so combine like 15 or 80 or 100 cells in a single stack, and then design the size of the battery. Typical energy to power ratios are like 4 hours or 8 hours. So this is the time, the discharge duration of the battery. So for day storage, typically 8 hours are provided here. So we have a great variety in life cycle inventory when we want to do life cycle assessment. We did some LCAs of vanadium flow batteries. And here you see an example that we did together with a manufacturer, Cellcube, who manufactures commercial vanadium flow batteries. So this is always for every battery type a very good data source to have meaningful LCAs and to be able to validate this. And this is just to have an impression. This is 20 years use phase with 20,000 cycles. And within this 20 years, we have a replacement of stacks and pumps after 10 years. So this is important for the LCA calculation. Yeah, you find these different stack concepts with different single cell sizes here. So what we learned in this case study was the manufacturer, who is acting as a global manufacturer and maintenance service provider for these batteries. What is important for LCA? It's important to look at the geographic locations. So where does mining take place, production sites, distribution, options, where is the use side, and where can recycling or reuse take place. So in this case study, we looked at sites in Europe, China, and Australia. Australia is important because it's a vanadium mining place. We have just little spots, mostly Australia and China, where we have vanadium mines. Then we have when we look at the use phase, Jens just said the use phase will be excluded in the legislation, but when we look at the use phase, the volatile energy input source is important. Is it wind power, photovoltaics, hydropower? This does affect the carbon footprint at least. And the system efficiency, of course, which might be between 70 and 80% for this type of flow battery. When we look at the results for LCA of flow batteries, we always see that the electrolyte has the largest effect on environmental indicators. And this is why we took a closer look on the vanadium electrolyte, because we found that this vanadium electrolyte causes very high emissions, but on the other hand, it's very, very stable. So it can be used on and on and on, and we do not need any primary vanadium to have a series of batteries. So this is why we thought that it is not fair to compare vanadium flow batteries with primary electrolyte to lithium batteries. Together with KIT, we did this comparisons, and we just found that this is not very fair. And I'm from a process engineering department, and that is why we developed a process to recycle or remanufacture the vanadium electrolyte. And we found that it is very simple chemical and electrochemical process, and we calculated the footprint for this. And what you see here on the left side, you see a benchmark which is by 0. 0 is the primary electrolyte, and we developed different scenarios to remanufacture or recycle this electrolyte after 20 years of battery use. And in all these scenarios, you see that we can reduce the carbon footprint of the electrolyte by 80 to almost 100%. So this means when you go to the right side here, when we have a cascade use of the electrolyte for flow batteries, the emissions for the whole battery system are reduced very dramatically. So in the first use, you see a reduction by like 40 to 50%. And this has to be taken into account, as we discussed before. The reuse and recycling of components has to be taken into account, and especially for the vanadium flow battery, these are very dramatic changes here. So we want to go towards a fair comparison of battery technologies, of lithium chemistries, of flow batteries, and towards a flow battery path, because these types of battery are, to us, they're very important, and they're by now somehow neglected by legislation, and we should change this. Flow batteries have these unique characteristics of independent energy and power, and so we have a variety of applications here, and the electrolyte that is used may be a game changer. So we did studies on these organic electrolytes, and when we have many opportunities to produce sustainable batteries in these fields. For when it comes to value chain and circularity, the criticality of raw materials has to be taken into account, and we can really vary the materials for the active materials and the stack and battery materials here. We have the remanufacturing and the reuse options of components, because we have this very long lifetime of the whole system here. And we should take into account the recycling and recovery of these secondary materials. And we see trade-offs in circularity and quality requirements. This is another point, because this is true for all types of batteries. We have very high quality requirements when we look at electrochemical devices. And so if I could make a wish, I would like to integrate the quality of secondary material to LCA. Thank you.
Thank you, Christina. Thank you very much. I'm seeing now Mr. Rana Pant from the Directorate General for Environment of the European Commission. So we have two speakers now to lead the floors, and we have more or less 20 minutes. So I would kindly ask you to concentrate, to reduce a little bit the time allocated, in order to avoid to lose nothing from both speakers. So I would start with Mr. Rana. Please, can you share the screen? If you want.
Okay, thanks very much. Apologies that I joined late. I really completely forgot about this, and I basically got up 1 hour before from bed, so I'm not feeling well. I'm happy to go last, that the other person has a better chance to present, because, I mean, yeah, my bad. So.
Thank you, Rana. Thank you. You're so kind. So we can skip to Johannes Lindorfer or Eva-Marie Heigl from Energie Institute of the Linz University. They will talk about the evaluation of sustainability in the hybrid sector. So thank you for joining, and please, if you can reduce of 1 to 2 minutes, we really appreciate.
Yeah, thank you. Thanks a lot. Thanks a lot for the kind introduction. My name is Johannes Lindorfer. I'm working for the Energy Institute, and I'm here with Eva-Marie. We have been, it's our first time to be in contact with that working group, and it's really our pleasure. So as the time is running, I will probably most likely skip a lot of the introductory slides in terms of why are we doing all this, because you are absolutely aware of all the things that are relevant here. With that graph, I just want to point out, if we are as a university working on accompanying research for product development, we very often start with, let's say, a rather simple stakeholder approach in order to gather all the engineers from the development departments of the partners, but also from research, but also company sides, in order to work on those principles for implementing a circular economy. So we really see this as a first quick win to go with relevant stakeholders through all the options on the product level, on the battery limit level, in terms of looking at what to do to refuse, rethink, reduce, repair, remanufacture, refurbish, reuse, recycle, and repurpose a certain technology implementation. True for all the storage technologies that we have been looking so far onto. And this is some sort of a first quick win that we normally apply in order to look or also a bit educate people out there in the manufacturing world or the process development world in order to onboard them on that circular economy principles. Then when we have that sort of engagement realized, we are looking at the sustainability analysis itself. As mentioned before, the methods are out there. It depends always on the research question, which methods we as a working group apply. And these numberings are basically referred to some sort of the recipe or the approach that we follow. So where are we? Are we at which level? At the company level, at the supply chain level? What is our temporal resolution? What is the required data to provide our input and output balance? And what is then needed additionally for the completeness to really provide educated results here? As mentioned, okay, life cycle assessment is one option or one method for that ecological footprint, but also quite relevant is that stakeholder approach to really more or less dive into the needs of the specific technology owners, but also probably the users. So we have also probably the linkage partly in our work to the other task force on social sciences and humanities in terms of trying to get information via interviews from all the relevant stakeholders on such a value chain. So qualitative and quantitative is, in our point of view, quite essential. Yeah, and for the LCA, it's quite clear. You have already said we have already seen from the previous speakers that this cannot be done, let's say, in a simple way. It's always about that LCA twin, the digital twin. And with that, very short introduction, I would like to hand over to Eva-Marie. She basically did a life cycle assessment on a hybrid energy storage system, so coupling vanadium redox flow battery with a supercapacitor. This was funded via an European project, and we did a lot of different scenarios and so on. Eva-Marie, please follow on, and I will move the slides.
Thank you, Johannes. Yeah, I would like to present to you the results of our project that we took part in over the last about 3 years. It's called High Flow. And as Johannes already said, it's about the hybridization of vanadium redox flow battery with a supercapacitor. So the advantages of this system are a little bit, you can say, both of the best of both worlds. So it's the dynamic handling of high loads through the supercapacitor on the one hand, and on the other hand, the large storage capacity provided through the VRFB. As we already heard from Professor Minke specifically, it has a good scalability and independent scalability of power and energy, and also the advantages of fast discharging and charging. So possible applications would be, for example, peak shaving of mid and short duration power peaks, renewables balancing, grid stabilization, and so on. What we did as an energy institute, we monitored the development process through life cycle assessment. We identified environmental hotspots in the production process and gave recommendations to our project partners on sustainable material and energy choice. We tried to specifically, can you go back one slide? Sorry, Johannes. We specifically tried to focus on sustainable material choice. For example, we used locally sourced activated carbon electrodes for supercapacitors, water-based supercapacitor electrolyte, no critical materials in the supercap. And of course, the VRFB electrolyte is non-flammable, which is a big advantage. And we also demonstrated a recycling process of spent vanadium electrolyte and many more. Thank you. We did the LCA for all the life cycle phases of the HES system, which starts with the production phase. So really starting from the very first starting point of mining. What we find out, as already showed in other publications, is that the VRFB, or the vanadium pentoxide in the vanadium electrolyte, causes the largest share of impacts for the vanadium flow battery, and the vanadium flow battery causes the largest share of impact of the overall HES. So also here, the vanadium pentoxide has the highest impact on the overall system, so the vanadium pentoxide production. On the other hand, the impacts of the supercapacitor on the HES production were almost negligible. So the single parameter that has the highest influence on environmental impacts of the HES production is the storage capacity of the VRFB, which is determined by the amount of vanadium electrolyte. Okay, thank you. Next. For this reason, we had a closer look at again at the vanadium electrolyte, applying also data that Professor Minke will know very well from her group. So we looked at different LCA datasets for primary and secondary vanadium pentoxide that are available in literature, and they show a very wide range of results. For example, datasets by Blume et al. Or Weber et al. Start with the mining of titanomagnetite ore in South Africa and further processing in an electric arc furnace. However, if you look at the graph here on the right side, the global warming potential per kilogram of electrolyte with these two different data sets is very different. So the first one is 11.4 kilograms CO2, and the second one is just 1.1 kilograms CO2 per kilogram electrolyte. So there's a huge difference. From our point of view, the first data set by Blume is the most accurate and suitable data set for high purity vanadium pentoxide from South Africa at the moment. We saw that the choice of the vanadium pentoxide dataset has a very high impact on the production of the vanadium flow battery. So next, I'm coming to the use phase. For the use phase, we calculated the application for a real case of peak shaving of short and mid-term consumption peaks in industry in Germany based on a real consumption profile. And we saw that electricity losses during charging and discharging of the HES caused the highest impact on the global warming potential of the use phase. When the HES is charged, for example, with European grid mix, conventional grid mix, or with photovoltaic power. On the other hand, the exchange, for example, of the supercapacitor after 10 years is almost negligible in this case. And as to be expected, the impact of the use phase can be drastically reduced when you charge the HES with renewable energies instead of conventional energy sources. The end of life phase, for the end of life phase, yeah, this is quite a difficult part, I must say. I made many assumptions, and yeah, I'm sure you could assess some points in a different way, but I assessed for the recycling. I modeled recycling for the vanadium electrolyte and for the metal parts, and for other parts like plastics, I modeled waste combustion with energy recovery. And I also modeled the end-of-life phase with and without credits for recycled materials and recovered energy from waste combustion. Yeah, as you can see on the right, you can achieve a total negative impact of the end-of-life phase if you apply credits. And this again stresses the importance of recycling at the end of life. And eventually, we combined the life cycle assessment of the 3 phases for the entire life cycle. And we see here in 12 scenarios that the production of the VRFB and specifically the vanadium electrolyte has the highest impact on the global warming potential of the entire HES life cycle in most scenarios. Only in the scenarios where the HES is charged with conventional grid mix, like in 4, 7, and 10, or in the scenarios where we modeled the HES with recycled VRFB electrolyte, then the production of the VRFB is not dominant. Yeah, as I already mentioned, the selection of the vanadium pentoxide dataset and also the choice whether you use primary or recycled electrolyte has a huge impact on the results. What were the main challenges and what are the further research needs in our opinion? Yeah, you have this wide range of possible results depending on how you calculate it. Then also the lifetime of HES components and the lifetime of the HES itself plays a very important role, because early failure or underestimation of the lifetime can lead to completely different results. It is very important to adapt the HES to the use case because, and specifically regarding the storage capacity, because this is the one parameter that mainly determines the environmental impacts. If you want to implement VRFBs and or a HES system in the European energy system, it would be necessary to ensure and also advance a circular economy for vanadium electrolyte. It would be very important to develop an average harmonized LCA dataset for primary vanadium pentoxide on global and or regional level, as already suggested by Blum et al., and to further assess other secondary vanadium pentoxide sources in Europe and evaluate their environmental impacts. Thank you very much for your attention.
Thank you.
Thank you, Johannes and Eva-Marie. So now we can move to Rana Pant, just to have a conclusion regarding the battery regulation and linking with Jens Peters said before as the initial part of the workshop. Please, Mr. Rana, if you wish to share the screen.
Yes, I hope you see the PowerPoint presentation now.
Not in presentation mode.
Okay. Well, now I hope it's better readable. Yeah. So from my side only, again, apologies for being that late and honestly that unprepared. It's basically...
Sorry, I see the presentation mode. So the one with the like this where you see the next slide for the presentator.
Okay, I try to take that out. And hope that you now see just the slide.
Not yet.
Wow, that is bad.
But also without presentation mode, the presentation was readable. So if you want to go through each slide,
please, if you otherwise don't see anything, that is strange. So I hope that at least now you see this slide again, even if in presentation mode. So it's about the battery regulation.
Not yet. The slides are not.
The presentation is not on. No.
No.
But also without presentation mode, the presentation was readable. So please go as comfortable. Okay.
Okay.
Okay now, yeah.
Sorry for the hiccups. Why is the batteries regulation necessary? It's simply, as you will all know, that there will be a huge, you almost can say, explosion from the demand side compared to the current situation. And that basically, I hear at least some background noise. But okay, I will continue. And it's
Please, can the audience unmute? Because otherwise we have a background noise.
Or to mute, to be honest. So it's reducing the dependency from fossil fuel and, of course, accelerating the transition. We need to basically, with the battery regulation, harmonize the common efforts that the transition towards the renewable energy path happens in a similar harmonized way across all member states, that they go into the same direction. And of course, that in general, the circular economy will help to shift the security of supply for raw materials and energy and enhance our autarky, basically, on the energy side. What is in scope of the battery regulation? It's basically took a very broad scope, especially compared to the battery directive from 2006. So we have the portable batteries, starting lightning ignition, SLI batteries, formerly automotive batteries, light means of transport batteries, electric vehicle batteries, and where most of the discussions were about so far, industrial batteries as well. What is in scope? In scope is basically everything. It's the entire life cycle, really from the natural resources, the mining processes, over the entire manufacturing process, recycling, reuse if possible, but then as well the collection and disposal in terms of hopefully a lot of things will be reused and recycled first. There are a lot of targets in it. I will come to a few later on. What I think is important to understand is the first time that basically, at least on EU level, such a legislation tries to cover the entire life cycle, all the stages of a product, and as well tries to go into a lot of, let's say, areas, different areas, so environmental areas, production area, hazardous materials, recycling, but as well performance criteria during the use, and due diligence on how do you get your raw materials. So it's a pretty comprehensive set, which of course doesn't make it easier to implement. Some core elements related to circular economy. It's basically in chapter 2, we have the recycled content. We have also the carbon footprint, and of course where LCA then plays a role. And in chapter 8 on the management of waste batteries, we have recycling efficiency targets amongst other, and targets for the recovery of material. If I then go into the timelines for the recycled content a little bit, it applies to a range of batteries, of course, not to portables, but let's say to the bigger ones, industrials, SLI and EV. We have here the situation that it's clear that battery manufacturing waste and post-consumer waste can be a source for recycled content. And it's a staged approach. So you first have to have the calculation methodology, then you have to have the declaration of recycled content, and only then you have minimum targets basically kicking in. And the whole timeline is spans basically from 2026, which is very soon. And the first basically information requirements kick in 2028, and it goes on then with harsh thresholds with minimum recycled content kicking in from 2031 up to 2036. So quite some time for industry and stakeholders along the value chain to adapt. On the recycling efficiency, we have a similar but not the same, of course, picture. It's something where we are more used to dealing with it. We have here highlighted in red recycling targets for lithium-based batteries of 65% in 2025, so basically next year, and already 70% in 2030. And then you have the recovery of materials targets for the basically critical raw materials, if you want, cobalt, copper, lead, lithium again, and nickel. And lithium is again highlighted because that's kind of the new kid on the block, basically, and touched as well with some uncertainties. And as well here you have you see some timeline that basically early next year we will come up with a calculation methodology, hopefully, and the targets kick in 2026, and then luckily, I have to say, there are possibilities, there are flexibilities built in already in the battery regulation that you can see after an assessment, and where it is justified. You can basically suggest, or we as Commission can basically suggest new targets for existing ones, so amend targets which are already there. Or basically as well, without a timeline, we can introduce new battery chemistries and attach targets to them, or we can introduce targets for recovery of material for those materials which simply are not yet captured by the battery regulation.